All right, welcome to this week of GROOT. Today we'll be hearing from Torgeir Aambø on KN local synthetic spectra.
Thank you so much. And it's a pleasure to be back in the GROOT seminar. Yeah, I will talk about a current and kind of ongoing project. We're nearing kind of the final stages on KN local synthetic spectra, and this is joint work with Marius Nielsen from NTNU in Norway. So I'll try to tell you a couple different things to kind of reach the goal, which is kind of progressing downwards on this little list. First, I'll try to introduce synthetic spectra, which is a fun theory in itself and deserves to be talked about a lot. I try to be like relatively brief and to get like to the fun and new part. And since we're gonna be using some chromatic homotopy theory to inside the category of synthetic spectra, so we need some knowledge on chromatic homotopy theory. So I'm gonna try to give a brief like crash course on chromatic homotopy theory for those who don't know this yet, so that we're just speaking the same language and have the same fundamental understanding. And then this chromatic crash course gonna introduce two ring objects, which I will denote En and Kn. These are kind of the famous chromatic gadgets that we have available to us, which is Morava E theory and Morava K theory. And we'll look at the synthetic spectra based on these two ring spectra. And finally, I'll try to explain that kind of synthetic spectra based on En is a very good and natural category from certain viewpoints. The category of K and synthetic spectra is also a good category to study in itself, but it's kind of the wrong category to study for some perspectives, at least the ones that I am interested in. So I'm gonna introduce a fourth kind of mix between these two, which is the so-called KN local synthetic spectra category. This is the kind of the new construction that we're exploring in this joint work. So I'm gonna try to list some properties of these KN local synthetic spectra, and then finally, if time permits, yeah, if people want to hear about the Adam spectral sequence, then we'll try to say something about what is the natural Adam spectral sequence inside of this category of KN local synthetic spectra. So that's kind of the goal for this this talk. And of course, if anyone has any questions, just feel free to interrupt me and ask anything. And I'm guessing one of the organizers will pay attention to the chat. I can try myself, but yeah.
Yeah, I don't know if you mentioned that exactly because you saw that there's a question in chat right now.
No, I didn't.
Is the Balmer spectrum of any category of synthetic spectra known?
Yes, but not published, I think. So this is a joint or ongoing project of Robert Birkeland and some guys. They gave a talk on it sometime and never got around to writing it up or publish it, I think. But yes, but no, but yes.
Thank you.
The vague answer. The correct answer is send Robert Birkeland an email and he will perhaps respond. Okay, so this is the rough plan. So we'll start at the beginning with introducing synthetic spectra. And all of these things I'm gonna say in this section is based on work of Piotr Prusakowski. I'm gonna do the little twiddle on the A thing, which I don't know what it's called, but it's in the name. Yeah, so all of this can be found in his work, which is called like synthetic spectra in the cellular motivic category, which you can find by Googling. Okay, so what is a synthetic spectrum? So the kind of basis we need for a synthetic spectrum is some other spectrum. So I'm gonna choose some nice spectrum, which I'm gonna call R in the category of spectra. And I'm gonna let it be an Adams type ring spectrum. So this will be a standing assumption on all of the spectra that we will base our category of synthetic spectra on. This will be like an Adams type ring spectrum. And if you want, you can assume like strong commutativity as conditions on R. For example, some of the spectra we'll see later will be like E infinity ring spectra, but some of them will also just be E1. So any like homotopy associative ring structure, it should be fine. And this Adams type condition, if you don't know what it means, it's just like a technical condition to make things work out in some like edge cases. So this is just like a technical condition that makes things nicer. So if you don't know what it is, just think nice ring spectrum. Okay, so let's make the first definition, which is what is a synthetic spectrum based on R. So on R-based synthetic spectrum is a spherical sheaf and I'll explain some of the terminology here in a second. We should have an up. Okay, so what are these things? This category here, or this site. So SPRFP is the site of I'm being pedantic and detailed about this first definition so that we have this category of synthetic spectra clean on the board. So it's the full subcategory of finite projective spectra, where this where we also require that these objects in SPRFP with finitely generated are homology. So this is a long definition kind of, or if you haven't seen it before, it might seem weird that we're kind of choosing some weird site of spectra, and we're studying sheaf of spectra on this category. This might seem weird at first, but this requirement that they have finitely generated R homology, this is really like the magic which makes synthetic spectra a really interesting category to study. So we're going to denote the category of synthetic spectra based on R. So the category of all of these sheaves. It's like the sheaves, so spectra, and the spherical condition just means that it's an additive functor on SPRFP. Okay, so this is the definition of the category of synthetic spectra. And the kind of the goal of the next couple minutes will just to say why is this an interesting definition? Why does people care about this? And kind of what does it give us? Okay, I'll do this maybe. Yeah, I'll also need another notation just in case I'll need it. So I'll also put a hat on the S if we take hypercomplete sheets. This is the subcategory of hypercomplete sheaves, or this is localizing at some class of morphisms. Okay, so the most important part for us about this category of synthetic spectra is, of course, its properties. And Piotr in his original work, and also people later, have used this category to do a bunch of very interesting results. So let us do like a mixed theorem / properties. And all of these are in in Piotr's paper. Okay, 1. There's a fully faithful co-continuous embedding. New from the category of spectra to the category of synthetic spectra. And this, if you want kind of to understand what this does, then you take, this is defined as doing first the Yoneda embedding into all sheaves of spaces. So SBRFP, not spectra, but spaces, or anima, or whatever your favorite term for this infinity category is. And then, yeah, doing the Yoneda embedding, and then doing the sigma infinity plus construction. So this is either the definition or a result, depending on how you view the lineage of these things. And this we will call the synthetic analog. So I can take any spectrum and I can kind of embed it into the category of synthetic spectra, and I can study what happens in this larger, bigger, more technically complicated category. And I can kind of study the effects of what happens in the category of synthetic spectra, and I can kind of try to view or get information about normal spectra out of this construction. So if we want to think about kind of homotopy theory, or at least stable homotopy theory, as studying the category of spectra, then this embedding shows us that if we can study some properties inside synthetic spectra, then we can often learn a lot about spectra themselves. This is kind of a philosophy that has been used a lot during the recent years, both to do like new computations on, for example, the stable homotopy groups of spheres, which are technical and very complicated computations. But you can compute kind of a lot of extra stems, for example, by using synthetic spectra instead of normal spectra, and other constructions, which we'll talk more about in a couple of minutes. Okay, that's the first and very important part, that we have this fully faithful embedding. And we also have, if we instead go to the category of hypercomplete synthetic spectra, then there's fully faithful co-continuous. And this is just restricting the previously defined functor. I can take the category of R local spectra, and I can embed it into the category of hypercomplete synthetic spectra. This is just a remark, or maybe not its own point. It's like 1.5 or something. Okay. So that's just if we restrict to hypercomplete things, then we can't fully embed the whole category of spectra, but we can embed the part of spectra that's kind of localized around the homology theory R. So we see only information up to this R homology theory, which is this category of R local spectra. Okay, some properties about the synthetic category itself. So syn R is symmetric monoidal, presentable, compactly generated, stable infinity category. The unit under this, I will write the symmetric monoidal structure just as a tensor product. And the unit under this symmetric monoidal structure, the one is the synthetic analog of the sphere spectrum. So you just take the unit in spectra and you send it through this synthetic analog construction that I defined here. And this is the image, or this is the monoidal unit in the category of synthetic spectra. But this new construction, so it sends the unit to the unit, but it's not a symmetric monodal functor, not in general. And so this is just a side note. Is not. It's not symmetric monoidal in general, even though it might look like it because we have this image of the unit is the unit condition. But it is lax monoidal, so it's not symmetric monoidal, but lax. Okay, this unit, so I will also sometimes maybe denote this as S00, which will become apparent in just a second. So there is an endomorphism of this unit object. Which is often called tau. So let me see how I will I haven't explained the grading here, but this tau morphism gives the category of synthetic spectra an extra grading. So it's a stable category. So it has a like in categorical suspension functor. But it also has this synthetic analog. So you can embed the suspension of the sphere or the desuspension of the sphere by using this synthetic analog, and you can kind of try to compare these two. So this is the synthetic analog of how will I write this? The suspension of S minus 1, and this is the suspension of the synthetic analog of S minus 1. And this comparison between these two objects just tells us that this and this endomorphism is not an automorphism. So this synthetic analog functor does not send loops to suspensions or suspensions to loops. And this tau morphism kind of tells us how far apart these two are. So this internal and external suspension is kind of two different constructions. And yeah, this tau tells us how much they differentiate or how much they differ, and also kind of makes this whole category a bigraded category. So for any spectrum X, there's a map tau given by just tensoring with, so how do I want to say this? So tensoring with this map tau from this the sphere of grading 0, -1 to 0, 0 makes the entire category a bigraded category. Since this S00 is the unit, so you just get an extra grading. Okay, so this is one of the also both technical but also a very important parts of this category. It's not just a stable category, but it has an extra grading, which allows us to control a bunch of the information that we want to study using these synthetic methods to study the category of spectra. Okay, so this allows us to do several different things. This endomorphism, so we will call, so tensoring with tau makes in bigraded. So there's some exactly like a map from X to X, omitting gradings for any spectrum or any synthetic spectrum X. And we call the subcategory or these synthetic spectra such that tau acts invertibly. We call them invertible or tau invertible. And we can construct a underlying spectrum functor. So tau -1 from the category of synthetic spectra to spectra. Given by inverting. Now, this can be made, of course, very precise. I won't go too much into the details, but it turns out that the full subcategory of synthetic spectra, such that tau acts invertibly, is equivalent to the category of spectra. And this tau -1, this inverting tau functor, is given as the it's not a adjoint to some nice construction, but it's almost kind of a left adjoint to this synthetic analog, but not quite. It's left adjoint to the spectral Yoneda embedding, not this new that I've introduced earlier, but yeah, it's close enough. And it's close enough in the sense that if I take some spectrum X and I take the tau inversion of the synthetic analog of X, then this is equivalent to X. So it's close enough to being like an inverse to, or it is an inverse to the synthetic analog construction, but it's not an actual adjoint. If you want to make it an adjoint, you can do some business on taking only like a graded or connected component of synthetic spectra and stuff like this, but it's not too important for our discussion. Okay. 5, I'm just listing some important properties. So there's a natural T-structure on syn R with heart comodules over the Hopf-Algebroid R star R. And this technical condition I mentioned in the beginning, this Adams type ring spectrum condition, this makes sure that this comodules over R star R category is an actual Grothendieck-Abelian category. So this technical condition just makes sure that this is, Grothendieck-Abelian and not just some, I think it's probably always abelian or at least like an exact thing, but yeah. Anyway. Okay, I think this will be the last property that we'll do, 6. So the cofiber of tau, or this tau map from the sphere to itself, will be denoted C tau, like just for the cofiber of tau. It is an infinity algebra in synthetic spectra. And modules over this infinite algebra fully faithfully embeds into the stable category of R. So the stable category is not necessarily the derived category of R star R as a Hopf-Algebroid, but it's a construction that Javi introduced. So this is like Javi's category of the stable category of this Hopf-Algebroid. It was introduced to fix some technical conditions on the derived category of R star R. But we can make some finer adjustments, but under certain assumptions that I won't go through in detail, but these will hold in, for example, the cases we'll be interested in later. So for example, if the ring spectrum is Landweber exact, but there are weaker conditions, then this is not just a fully faithful embedding, it's an equivalence. And modules over C tau is equivalent to stable R star R. And 6.5 is if we take the hypercomplete version of this, then the cofiber of tau is again an infinity algebra, but then modules, so in the hypercomplete setting, then modules over the cofiber of tau is equivalent to the derived category of R star R. So yeah, just hypercompleting. I guess I can write this like this or something. So hypercompleting this category as a subcategory of synthetic spectra just gives you the hypercompletion of this guy, which is this. But this is in fact true without this extra assumption. So this is a kind of a nicer statement that if you restrict yourself to hypercomplete synthetic spectra, then this modules over the cofiber tau is always equivalent to the derived category of R star R. And for those who don't know this category, it's just yeah, this comodule category I mentioned. R star R. This is a Grothendieck-Abelian category, and you can take its derived category, and this is this guy. Okay, that's a lot of properties, but we can summarize these in kind of two diagrams. So I can do the global one first. So the category of spectra fully faithfully embeds into synthetic spectra, and you can invert tau. And this composite is the identity. And you can also tensor with the cofiber of tau and form modules over C tau. And this fully faithfully embeds into stable R star R. This composite is yeah, given by the by R homology, or rather it's R homology and then including this into the stable category. So this gives like a very nice picture on what we can do with this category. You can both take the category spectra, embed it into the category of synthetic spectra, and then come back again by inverting tau, or you can go to an algebraic setting by tensoring with the cofiber of tau instead. And this is the same as studying these R homology theories on synthetic spectra, or on spectra, sorry. So this is the global setting, and in the hypercomplete setting, then we have the category of R local synthetic spectra, now our spectra, and we take the category of hypercomplete. This is fully faithful. And we can invert tau again. The composite is still the identity. We can tensor with the cofiber of tau to go to the category of modules, and this is equivalent to the derived category of R star R, and this composite is still given by R star homology. Yes, and let me see. Most of these are left adjoints. So this is a left adjoint, left adjoint, left adjoint. The identity is the identity. Okay, so this brings us, these two diagrams is at least how I like to think about synthetic spectra. And I like to focus on the hypercomplete setting because that's more interesting to things I care about. Because having like these local structures in at least in chromatic homotopy theory is more interesting than having the global one. Even though the global picture is kind of what we want to actually compute things about. Okay, so I've said some things about synthetic spectra. Let us like understand which homology theories are that we will use in the setup, which requires like a quick crash course on chromatic homotopy theory. So crash course on chromatic crash course is CCC. Okay, I'll be more brief here than I was at like introducing synthetic spectra, because the synthetic kind of theorems and constructions is more important than this part. Just a background for which rings we will be interested in. Okay, so someone in the chat asked about the Balmer spectrum, so let me try to do some Balmer spectrum introduction of chromatic homotopy theory. So in normal algebra, we're familiar with the spectrum of the integers. This is the spectrum of the integers. Down here, we have the generic point, which is 0, and we have 1 point for every prime, and we have an infinite amount of primes. So this is like a nice thing one can study in algebraic geometry and stuff like this. For spec C, or equivalently, if we want to think about Balmer spectra, which we'll do in a second, then this is almost also the Balmer spectrum of the derived category of the integers. Yes, okay. In this setup, we can describe some both like group theoretic, but also algebraic geometry type things. We can do localization and completion, which is kind of the two most important things we can do with primes or with these things. So we can localize at the p local integers, and we can localize at Z mod B. So if we do this in this Balmer spectrum or Zariski spectrum, depending on how you want to view things, then localizing at the p local integers is like choosing your favorite prime. So if I do say p equals 3, then if I localize at C mod 3, then this chooses just this part of the spectrum, and we work only on like locally around this. So localizing at these p local integers at some favorite prime is like choosing p plus this generic point 0. Okay, and we can also localize at this Z mod P, and this is like completion at P. So this means essentially, since the point P in itself is not a Zariski open subset of spec C, but we can form like a formal neighborhood, which is not a open subset, just like a formal open neighborhood around P, and completing any, like, for example, quasi-covariant sheaves over this spectrum, which is equivalent to the category of abelian groups, just means that we'll p-complete this abelian group. So restricting to this completion or this formal neighborhood around P just means completing your quasi-covariant sheaf. Okay, this is kind of known from, hopefully known from algebraic geometry. So this is AG. Okay, and in the world of spectra, then we have way more primes. This is complicated for some, but also more interesting. I'm just gonna draw the Balmer spectrum of the category of spectra. Looks roughly like this. Let me also connect everything, and yeah, it's also infinitely big. So down here we also have like a generic point, same as we have above, but here we have like the prime 2, but we also have a height variable n. So we have here the point 2,1, the point 2,2, and it goes upwards to infinity. And then again for the prime 3, we have the point 3,1, 3,2, blah, 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 3 infinity, and so on. So this is like 5 infinity and some p, comma 2, p, comma 1. yeah, so this description of the Zariski spectrum, or no, sorry, the Balmer spectrum of category spectra is by the thick subcategory theorem. Implies this. Okay, so now we have way more primes to play around with. So I'm gonna do like a similar kind of things. We can localize at different kind of objects. So we can localize that. I'm just gonna list some spectra. So these two are the spectral versions of these two objects. And what happens is exactly the same as it did before. Localizing at MZP just chooses some prime, say 3, and you restrict the whole Balmer spectrum to this part. So it's just choosing a column essentially and working only locally on this column. And the same thing happens at MZ, localizing at the spectrum MZ mod P, and this is completing at this column. So it's exactly the same thing happens. You form like a formal neighborhood around, but now you have more points. But yeah, it's essentially the same thing. But now we have this height variable to play around with that we didn't have in the algebraic geometry case. And we also have some spectrum, which I'll call EN. I won't explain what this is, but this acts, if I localize at EN, this acts on this Balmer spectrum as just choosing. So if I choose N to be 2, for example, and then localizing at EN is like choosing the column for P, but capping it off at 2. So I can also not only restrict to the entire infinitely high column, I can also cap it off at some finite stage. So this is like localizing at E2. And I can also do like a similar kind of completion thing that I did for a prime P above, but I can do it also at any of these like finite stages. So this is given by the spectrum Kn, so I can localize at Kn, and this is like taking some point and forming a formal neighborhood around this point. So if I Kn for some prime P, 2, for example, and n equals 1, then this is like completing at this point in the Balmer spectrum. So one can think about En and Kn as more refined versions of these two objects that we have available to us in classical algebraic geometry. Okay. That was quick, but also necessarily quick, kind of. And yeah, for the interested, then kind of things get more complicated as you move upwards in this ladder. So at this height 1 is where like complex K-theory lives, for example. At height 2, this is where like topological modular forms and things like this live. And above this, we have no very nice description of things. Okay. So let's do also a quick En and Kn synthetic spectra. All of the properties from before still hold, but there's a new kind of cool property that holds, at least for En, I'm gonna say something about. So I mentioned that this construction that taking first the synthetic analog and then tensoring with the coefficient of tau is like taking En homology or E homology. And doing this construction actually gives an equivalence between these two categories for certain very big primes. So you can use this construction that I did before. So theorem, this is also by Przygowski, but I'm gonna phrase it in a version that's kind of different. But it's inspired by work of Franke and also wait. Korea. Um, And yeah, I'm just gonna say it like this, I guess. For primes p much greater than the height n. So remember that this en is dependent both on an integer n, but also at the prime p. Okay, and this kind of equivalence is determined by this category of synthetic spectra. This category of synthetic spectra acts as a deformation between these two guys. This is kind of what we saw before. So En, and then you have this category of hypercomplete En-based synthetic spectra, and then you have the category of derived category of E star E. So this is given by inverting tau, and this is given by a tensoring with a cofiber of tau. And in this very nice situation, then both of these include and actually become equivalent. So a natural question to ask, since we have this this other spectrum Kn. So what happens for Kn? Then we also get a diagram like this. We get hypercomplete Kn synthetic spectra, and we get the derived category of Kn star Kn. But in this situation up above, where we have P much greater than N, one of the important factors that happen here is that this category of comodules over E star E is a finite cohomological dimension. And unfortunately, this is not true. And so this comodules over, I'm just going to write K star K, is not of fin cohomological dimension. I can explain later to those interested why this is not the case, but let me skip this right now. But this means that we can never get this the same kind of equivalence as we did above, because this really uses like this finite cohomological dimension property. And at least I don't know how to get around this in this K-based synthetic spectra case. But luckily there's a fix, and now we come to the meat of, or the I guess I don't have long left, but this cool category of local synthetic spectra. I don't remember where I'm in the list, but before maybe. Okay, so I can, this is essentially the definition, but we can form the category of synthetic spectra based on Morava E theory, this En. So I form syn En. I can even take the hypercomplete version just for niceness sake. And I can do Bousfield localization at the synthetic analog of Kn. It turns out that this category is very nice and interesting, at least for these couple things that I care about. So this is the category we call Kn local synthetic spectra. Okay, so I'm just gonna quickly say that we also get like a fully faithful embedding from Kn local spectra into this category. Which also has this. We also have an endomorphism of the unit, which inverts, and you can prove that. Okay, let me say this differently. You can prove that the tau invertible objects in this category is exactly like the Kn local spectra. So if we do like LKN syn E, and then we take those objects which are tau invertible, then this is the category of KN local spectra. And similarly, we have a cofiber of tau, or C tau hat maybe, and modules over this category, modules over the cofiber of tau, is some nice category that is kind of related, or it's the derived category. It's almost like a derived category or something, but it's not the derived category of E star E comodules, but it's the those comodules that are complete with respect to some, to the M is in the homotopy groups of E. This is like a regular local Noetherian ring. It has a maximal ideal M, and you can complete at this ideal in some nice way. And the category of modules over the cofiber of tau is equivalent to this category. And this allows you to prove a version of this deformation statement that I had before, this equivalence between the two categories. This is a theorem by me. And this also gives us an equivalence between the homotopy category of KN local spectra and the homotopy category of this completed E star E comodules. And this also only true for primes P much greater than height N. Okay. Yeah, I don't think I'm gonna say much more about this. I can just note at the end, because I'm out of time, that for those who know that this category of synthetic spectra also acts as a deformation of the Aldrin spectral sequence, or a categorification of the Aldrin spectral sequence, then there's a natural Aldrin spectral sequence in the category of KN local synthetic spectra, and has natural and after inverting tau, so this is like looking only at the actual spectral parts, like taking the underlying spectrum functor, is the normal KN local EN Adams spectral sequence. Okay, I think that's all I'm gonna say. Thank you for your time and for your attention.
Great. So let's thank the speaker for a great talk. And are there any questions? Right. So if not, then let's thank the speaker once more. And I'll stop the recording.